therefore, it's a great pleasure for me to talk about a new loudspeaker technology that we developed at Arya Audio Labs. My name is Artur Marke, and I'll be talking to you about the loudspeaker invented, and we'll introduce this revolutionary loudspeaker driver. Just a few words about myself. I'm an audio researcher from UK. I studied electrical engineering in Germany, followed by master's degree in acoustical engineering in UK at the Institute of Sound and Vibration Research, where I also spent some years afterwards to work on nonlinearities in loudspeakers, which I guess also led to the development of the driver, which I'll talk to you later. My professional experience includes work for Apple in America, so I've done developments like iPhones, AirPods, and other audio-related developments there, as well as for Cirrus Logic and Wolfson Microelectronics. And, well, I'm really glad that actually I could use my passion for audio and create my own company and do something that I hope that you as audiophiles also appreciate, and as much as I do. To start off with, I thought we just have a quick glimpse on the status quo, which is basically the dynamic driver, since the limited time that we have. Obviously, we're surrounded by loudspeakers, especially here, the high end, and the vast majority of them is based on the technology of the dynamic driver, which is technology developed in the 1920s. And still around because it's such a simple technology. It's easy to implement and easy to mass produce. And there isn't really any technology that has since really was able to get away the status of the dynamic driver. But it has its problems. Obviously, back in the 1920s, they didn't care too much about nonlinearities, and they were happy that it was playing at all, I guess. So, but it has quite some drawbacks. So let's start with some of them that you're probably aware of. So one of them, for example, power handling. A dynamic driver uses something what is called voice coil. It's basically a thin wire that is moving inside a thin, narrow magnetic gap. And obviously, you want to keep the moving mass low. And this you can achieve by reducing the weight of the voice coil. And if you reduce the diameter of the voice coil of the driver wire, it can burn easily. So obviously, there's always a trade-off. You make the wire thicker, it can handle more power, but then it becomes less sensitive, so and can handle less power. So it's always a trade-off. Another thing is big topic, obviously, nonlinearities. I've studied for many years, and it's kind of hard to say just nonlinearities. I mean, there's so many different aspects for that. I will go into more detail later on, like what kind of nonlinearities they are, but let's leave that as a bullet point here. Then the limited frequency range. Obviously, ideally we want to have a driver that can handle from the lowest to the highest frequencies, but unfortunately, this ideal driver doesn't exist. So what we end up is to divide the frequency ranges into 2, 3, or more ranges where we have a dedicated driver that is taking care of that. This leads me also to the sweet spot problem. Obviously, those are kind of getting hand in hand. So you divide the driver basically in different frequency ranges, also because the driver starts to break up. So once the wavelength becomes smaller than the diameter of the driver, it does move as one piston. It starts to move not synchronized. And this will affect the output, obviously, of the driver. So you want to avoid it. And also, once you go up in frequency, the dynamic drivers start to beam. So you have a kind of a narrow beam that goes to higher frequencies. And this is something you probably see when you go to presentations here, the high end. People always try to sit like somewhere in the middle row, because this is where they expect you have the best sound, because this is like the equal amount of equal length, let's say, from the drivers, and you have the sweet spot basically. Once you move left and right, then the whole stereo image usually breaks apart, and you don't have the whole experience that probably the manufacturers want you to experience. Other thing is the sensitivity trade-off. As I said before, it goes hand in hand again with the power handling. So you make a diaphragm heavier to create basically to cover more area. yeah, it becomes heavier and then it becomes less sensitive. You do the opposite, and it's always a trade-off between those factors. So it's kind of easy to find a balance between those factors. So let's just say what are the causes for those effects that we saw. So what I mentioned before, cone breakup. So once the wavelength is smaller than the diameter of the driver, the cone does move as one part, but in different parts. We have low air coupling. What we can see is that the driver area that you can see is also the moving part that is actually responsible for moving air and creating sound. And with a structure of having a diaphragm and an attached voice coil, it's quite inefficient. You can try to make it stiffer, whatever, but at the end of the day, you have quite a limited area. So what you see is what areas basically moved by the driver. Nonlinear force factor, it's quite a technical term for you who are aware of that. What it means that the voice coil sits in a side magnetic gap, and it's not a static condition. So once you apply a music signal, it moves in and out from this magnetic gap, changing the magnetic field. And this, in terms, also changes the characteristic of the driver in terms of the frequency response. And it's also one of the very important nonlinearities in the driver. Another is the nonlinear stiffness. Obviously, you need to suspend the driver inside the magnetic gap. It cannot move left, right, otherwise it would have rocking and scratch sounds, etc. So you would need to restrict it from having non-pistonic movement. And therefore, you need suspension, spiders, and all those parts. They're mechanical, and they're not linear, unfortunately, either. And also adding to the nonlinear characteristic of the driver. Another point is the unstable characteristic during time, like over time. So you obviously see maybe a nice frequency response of a driver, but once you start listening for some time, those characteristics are no longer valid, because they will change due to the heat up of the voice coil. It's sitting inside a really narrow magnetic gap, which is not exposed to air, so it's kind of contracted. And by changing the temperature, you'll change the resistance. It changes the impedance of the system, and it, again, in turn, will change the characteristic of the driver. And the inductance is obviously another factor. Voice coil is nothing else than an inductor, and inductor has impedances. And what it is a frequency-dependent resistance. And no amplifier likes anything that is changing with frequency. And obviously, you wanted to avoid that, but since it's a mechanical system, which works with inductance, you cannot really avoid having resonances. So something that I wanted to show you here is a study by Floyd Toole, who was working for Harman many years and was responsible for a lot of cutting-edge research, actually, in the acoustic field. And something that I wanted to show here is one of his slides, actually, that I think is quite important and shows the problem that we have with dynamic drivers, so in general with loudspeakers. Here you have a loudspeaker that actually looks pretty decent on axis. So this is the direct sound from the loudspeaker, and you think, oh yeah, that sounds like a decent loudspeaker. But what we often don't see is that the sound we perceive as listeners is not the direct sound. Is a combination of the direct sound and the reflected sound. And in fact, the reflected sound is dominant for the sound power, which is representing the perceptive sound. So what we actually should look at is the sound power. So if we see, for example, the early reflections, they look nothing like flat anymore, or the sound power, which is actually the closest you can see to your perceived sound of a loudspeaker. And this is definitely nothing close to a flat loudspeaker. And so this speaker would sound flat, would sound pretty terrible, actually, even though you would think that from the on-axis response, it should be a good loudspeaker. And this shows the paradox in the industry and also with the driver technologies that we have today, that we might assume we might do certain assumptions about the loudspeaker based on measurements that are actually not really relevant for the listening experience that we actually care about. So this was some of the reasons why we actually worked on developing something better. And this is why I wanted to introduce you this driver that we developed. It's called AirBlade. And this driver combines all the knowledge that we developed over the years about transducers, nonlinearities, and culminates everything into a driver which solves the problems that I actually showed you before. So let's just quickly see how it actually built up. I know it's quite a drastic change from this nice picture to this, but I thought it's probably easier to explain it in a simple chart. The main part of this driver is a diaphragm, which is ring-shaped, and it is stacked above each other. So this way, first of all, it radiates sound radially, so we don't have directivity issues. So it radiates at all frequencies, in all directions, in the same power. Second, we use the stacked arrangement because we can adjust the sensitivity. The more layers, the more sensitivity we have, obviously, with this driver. And this way we can adjust. So if we want to have more output, we can just add some layers and create more surface area, which obviously reduces distortion and other effects. And obviously, like any loudspeaker, it has a magnetic structure consisting of pole plates and magnets. And as you can see here, with 16 layers with a diameter of 11 centimeters, which is like the prototype that we also exhibiting in Hall 1 in B07, we can create a diaphragm area of almost 20,000 square millimeters, which is equivalent to 37 times bigger than a traditional 1-inch driver. And it has many advantages as well, I'll show you in a second. Here's a little close-up of the diaphragm structure. So you have layers of diaphragm material. It's probably hard to see. There's a transparent layers here that are probably a bit hard to see on this picture. But just getting back to the picture I showed you before. So we have layers of ring-shaped diaphragm and separated by little spacers, which we call blades. That's why also the name AirBlade. And what it does is, because it has conductive traces directly applied on those ring-shaped diaphragms, when you apply a music signal through them, it pushes air out or sucks air in, depending on the music signal. And this way, we can move a lot more air than with a traditional dynamic driver. And this leads to lower distortion and other effects, as we'll show in a second. At a glance, the advantages of this driver, so we can realize broad frequency range of this driver. We can cover way beyond below 1 kilohertz to above 20 kilohertz with a single driver. And the interesting thing is that you can use it with, if you want first order crossover at 1 kilohertz, and it won't burn the driver because we have so much surface area and so much conducting material, since we're spreading it over such a big surface area that the power handling is huge compared to a regular driver. And due to the fact that it's also exposed to air, and the more it moves, the more it actually cools itself. It's a self-controlling mechanism, you can say. The other thing that I mentioned also before, it doesn't become directional. Because we have this radial radiation, the driver is not dependent on the frequency. The radiation pattern is always the same. So whether it's you playing a 20 kilohertz signal or 1 kilohertz signal. And this is, as I showed you before, it's very important for the perceived sound quality, because the reflected sound will be as close correlated to the direct sound as possible. And it might sound not as important, but actually if you think about psychoacoustic, and we've done quite a lot of research also in that field, then this factor is actually quite important, because we as listeners are able to actually hear through rooms. So we can adapt actually to the room acoustics. It's based on a history of evolution where we actually had to adapt in different environments. And we have the capability of adapting our hearing to the room. That's our brain is quite powerful in that sense. And what it means is that if we have a coherent source that radiates sound perfectly on axis and off axis, we can locate this. We can imagine the actual source that was imagined by the artist much better than if it's not correlated as with the traditional driver that becomes directional with higher frequency, where you don't have as much correlation between the direct and reflected sound. So another advantage, obviously, the larger surface area. We can fit a lot more driver into a small space than with the traditional technology, and we can customize the radiation pattern, which is actually quite remarkable because I'm not really aware of any other technologies that can do that. So we can make a driver that has a directivity pattern of 180 degree, 360 degree, 90 degree, for example, for automotive, where you don't want to have reflections from the windows or the windshield. You just narrow it down. And you can really realize any radiation pattern that you want for a specific application. And for example, here we have on display a driver that has a 180 degree radiation pattern, which we found is the best for home applications because you don't want omnidirectional loudspeaker, because once it hits the back wall, you'll have something like it's called a phantom image, where you have a source perceived twice, once as a direct sound and once as a reflected sound from the back wall, slightly shifted in time, obviously, because of the time difference. It takes to bounce back and to the listener. So ideal for home audio applications, we think that 180 degree would be a good application, but yeah, we are not restricted to that. Another advantage is the linear phase and impedance. Since we don't have a coil in the sense that of a traditional loudspeaker, we don't have any inductance effects, really. It's a linear impedance and with no phase shifts, which is quite of interesting if you want to use if you want to use amplifiers, and yeah, it's really easy to handle this power, this driver. And yes, last but not least, obviously the high power, because we are spreading the conductive traces over such a huge area, we can quite handle a lot of power in that sense. Mm-hmm.
I have one question. You mentioned advantages. Are there any identified disadvantages compared to traditional loudspeakers?
Nothing identified yet, apart from it's a bit more complicated to build because we have a certain magnetic structure that we need to ensure enough magnetic field inside the gap. But other than that, I mean, it's just a technical challenge which we solved so far. Other disadvantages are not really known so far, and we've been working on it for many years already.
Okay, thank you. A second question.
Mm-hmm, sure.
You mentioned you can control the coverage from 360 down to 90 degrees. Is it possible to decrease it even more than 90 degrees, down to, for example, 45?
Yeah, no problem.
Okay.
Yeah, like any angle, I mean, obviously.
I'm thinking about telephone conferences where you want directional sound from different persons, for example. Okay.
Yeah, you just make it's like a cake, basically. You just slice it in the way you want it for your application, and you can just customize the design based on whatever application you have, and then tailor it to that.
Can this technology be adapted to less than 1 hertz, 1,000 cycles downwards?
Yeah. You ask whether it's possible to go lower than that?
Yeah, say for example 15 hertz to
you mean to make a low frequency driver?
Correct.
Yeah, it's
Correct.
possible. Yeah, you just change the width of the diaphragm, and then you can make as well a low frequency
and
driver.
that would be one driver.
You will have to change because of the, as I said, with the breakup. So you want to have the width of the driver that will dictate the resonance frequency. So with this driver, we use 8 millimeter width of the diaphragm, which gives us a resonance above 20 kilohertz. If you make it wider, obviously it comes down. So I would suggest to use a bigger, wider diaphragm area for lower frequencies, and then to change it to a narrower diaphragm for higher frequencies.
There would be no compromise on the sound quality by changing it.
Well, you just need to have a crossover with the regular. But you can use a first order crossover.
Thanks.
And actually, we use this driver without crossover as well, so you can directly plug it into an amplifier without burning it.
What does the impedance curve of this loudspeaker look like?
The what? Sorry,
Impedance curve.
It's flat. It's it's like a resistor.